At the beginning of our universe, a minute blob of time and space, far smaller than an atom, began to expand as a way of dissipating its extreme energy. Such three-dimensional spatial expansion that happens everywhere and all around us is well represented by this two-dimensional surface of a balloon that is stretching as it's been blown up. The Big Bang into pre-existing space is now seen as the big stretch of space itself. After a moment of extraordinarily fast expansion, the blob seems to have contained a plasma of particles, including quarks and gluons. Then, as the energy density lowered, it seems that the Higgs field came into being, giving mass to the particles. On further stretching, the quarks and gluons condensed into protons and antiprotons, which almost annihilated each other. But not quite. The few protons left over formed the basis of the universe we now live in. 380,000 years after the beginning, energy was low enough to allow electrons to surround the protons and neutrons and form the first atoms. This neutral environment allowed photons to travel in straight lines. It was first light for the expanding universe. 200 million years from the beginning, gravity began grouping the first stars into galaxies. The clue to the concept of the big stretch came from the observation that when we from our galaxy look at a nearby galaxy, it only moves away slowly, whereas a distant galaxy rushes away at breakneck speed, as you would expect if they were on the surface of an expanding balloon. By colliding particles in CERN's Large Hadron Collider, it'll be possible to momentarily produce sufficiently high energy levels to mimic conditions that existed billions of years ago. Observing the results will enable scientists to glimpse interactions never before witnessed. By visiting earlier epochs, the Large Hadron Collider will be taking us on a journey back in time. Back to the very beginning. At last, mankind will be standing on the brink of the birth of our universe.